discussion of precision and accuracy, you may be wondering, well, how do we begin to quantify those terms? How do we quantify the error, which results from inaccurate measurements or forecasts, and likewise the uncertainty in those measurements and forecasts? So we're going to talk about that now, and I'm going to present a couple of, or two examples, one for error and one for uncertainty. All right, just as kind of a review, you remember before, precision accuracy could apply to measurements like length, thickness, velocity, could apply to forecasts of future either natural events or also, and then in the third example, it could apply to something like what we call engineering objectives. In that case, you might think of, for example, specifications. So we're actually going to look at some design specifications for sheet metal manufacturing. We're going to talk about that. And just to remember, precision or a precise measurement is one that is reproducible. In other words, that you get the same value each time you do it. So in the context of sheet metal manufacturing, as we were talking about, you want to make sure that your sheet metal does not vary beyond some tolerances that you might specify. Accurate basically means that you have like a correct forecast or measurement, so that essentially like the mean value, if we were thinking of sheet metal, that the mean value rather than the kind of the deviations from the mean are accurate. So that if you want a 1/4 inch sheet metal, you're getting sheet metal that in the mean is essentially a 1/4 inch. All right, and here's, we looked at this before, it's kind of a metaphor for accuracy and precision. So what we're looking for, high precision, high accuracy. So you're hitting the target with very little spread, and that it's actually hitting in the center of the target. So it's hitting the correct values. Here would be a case of low precision, low accuracy. You're already, I'm not going to go into this in detail because we already discussed this graphic before, but it's a good one to keep in mind when you're thinking about precision and accuracy and what exactly it means. All right, so now let's get to actually quantifying it, and it's really, really basic and easy. So there are two terms we're going to be dealing with: fractional error and percentage error. So a fractional error is just the measurement error divided by the true value. So if you define that measurement error, you'd have the measurement minus the true value over divided by the true value. Of course, this presumes that we actually know what the true value is. If it's a measurement of, say, the length from here to the moon, maybe we don't know the true value, or maybe we have some generally accepted value we could use for that. But in the case of like sheet metal specification, yes, we would probably know exactly what the true value is, what we ask them to produce. So obviously a percentage, you just take a fraction, multiply it by 100%, and you get the percentage error. All right, pretty easy, right? The higher the measurement error, the larger your fractional error is going to be. Uncertainty. So uncertainty, remember before we were talking about essentially like confidence intervals, like we talked about it in some detail when you're talking about significant figures. So we said something like a measurement might be 3.25 meters plus or minus 0.01 meter. So that 0.01 meter, that's kind of like your estimate of uncertainty. It could be specified as a statistical goal. So you might say 99% of my measurements are going to be within that 0.01 meters. All right, so quantifying it, it's very simple. It's almost basically exactly the same as error. So fractional uncertainty is just the uncertainty over your best value. And the percentage uncertainty, you just take that fractional uncertainty already calculated and multiply by 100%. All right, I have two examples. One relates to the error related to hurricane forecast. The second of which looks at manufacturing tolerances and uncertainty in sheet metal manufacturing. All right. So the first one is we have expert forecasters forecasting the track of Hurricane Dorian from the Bahamas. Actually, in this case, the forecast was made before it had reached the Bahamas, and what direction it was going to take. And our expert basically said that the direction would pass this hurricane through Alabama, and in order to do that, it would take a track of 315 degrees clockwise relative to zero at due north. So if we have due north basically like this, going would be northward, 90 degrees would be in this direction, and so 315 is basically off in this direction. And you can see it would take us through Alabama, of course. And then later on, a few weeks later, someone looked at the actual track and found that the actual hurricane track was 350 degrees clockwise relative to zero at due north. Now we know that a full circle is 360 degrees. So the actual track was almost exactly due north. It was just shy. Due north would be kind of like extending from here due north, but 358 degrees might take it a little bit off to the west from due north. All right, so what was the error? We're gonna present that error both in fraction and in percentage. All right, so the fractional error, we take the measurement or the forecast value, subtract off the actual value, and divide by the actual value. And notice I always put the units. In this case, it's degrees. And you can see that the units essentially drop out and you end up with a fractional error. In this case, it's negative 0.120. And notice this last zero, why do we put it here? Because we have three significant digits, right? And so we're going to maintain 1, 2, 3 significant figures, excuse me. And this one, actually, the first one, that's a leading zero, does not count. All right, so how do we get from fractional error to percentage error? We just multiply by 100, and we end up with a percentage error of negative 12% for this hurricane forecast. Direction. All right, so let's go to the final example. And let's say we are a manufacturer, and we need to have manufactured for us a ferritic, essentially iron or steel-based stainless steel sheet metal part, and we need it manufactured. It's going to be 1,000 millimeters wide and a thickness of 2.5 millimeters. And we want to know what is the fractional uncertainty and percentage uncertainty. And we're going to use the tolerances from the manufacturer's specifications from V&F sheet metal. And I'll show you what those are in the next slide. So for example, they guarantee that they'll provide your sheet metal within a specified tolerance. So in this case, the tolerance is dependent both on the width of the sheet metal, so you see 1,000 millimeters wide, and the thickness. So in our case, we had a 1,000 millimeter wide sheet metal part, and we wanted it at a thickness of 2.5 millimeters. So the thickness tolerance, and that's in millimeters, is 0.11. So let's see how that translates to the fractional uncertainty, which is what we. All right, so let's look at the fractional uncertainty first of our sheet metal manufacturing. Our goal is to achieve a thickness design of 2.5 millimeters. V&F sheet metal tells us that they can get that to a plus or minus 0.11 millimeter. So the fractional uncertainty is simply that uncertainty, 0.11 millimeters, divided by 2.5 millimeters. And we end up with a fractional uncertainty of 0.044. And then we might want to see that presented in percentages. So I'll go to the next slide. And so the percentage uncertainty is simply that fractional uncertainty times 100%. We end up with the percentage uncertainty equals 0.044 times 100% equals 4.4%. So that ends our discussion of quantifying both uncertainty and error in either measurement, estimates, forecasts, or design specifications.